Today we will be going over section 4.6 and we're going to be talking about rectilinear motion. That will be motion walking along a line. So if the position equation for an ant that walks along a number line is given by S of t is equal to 2t minus 4, complete the table, graph the position versus the time, and sketch the actual path on an S number line. So my position function is given to me by this formula right here. S of t is equal to 2t minus 4. So when I plug in 0, I get negative 4. And what that tells me is that at time 0, my ant is right here, located at a position of negative 4 on this S number line. Right? Once we plug in 1, 2t, 2 times 1 is 2, minus 4 is negative 2. So you can see that we are walking to the right, and we end up here at negative 2. And then once we put in 2, we get 0, and we're at 0 here. Okay, and then when we put in 3, 6 minus 4 is 2, and we're 2. Right, so this corresponded to equals 0, 1, 2, 3. Every second that goes by, we seem to be moving 2 units to the right, and so then that you should see because this is a line of slope 2. When we graph the position versus the time, that is not the actual position of the ant. That's just graphing the position versus the time, right? And so this is your time. This is your position. 0, negative 4, 1, 2, 3, 4. So you are down here. At 1, you're at negative 2. And then at 2, you're at 0. And then at 3, you're at 2. Ooh, I missed that one. Three, you're at 2. And of course, the graph that you expect to see is a line. And get a straight edge, and you can graph your line. And there you go. Now in these problems, we're going to assume that the time starts at 0 and doesn't go to the left of 0, so your graph ends right here. And unless you're given a largest time, then we can continue to go to the right. S of t was 2t minus 4. So S prime of t is ds dt, the change in the position over the change in time, which is S prime of t, which is how far you're going divided by how long it takes you. So this is your velocity, and this is just going to be 2. The derivative of this term is 2, the derivative of a constant is 0, and you get 2. Right? And so because this is a positive 2, what this tells us about in the context of this problem is that my ant is moving at a constant velocity to the right 2 units every second. And that's what we were seeing right in the picture. Let's move on. And now we have if the position equation for an ant that walks along a number line is given by S of t is negative 3t plus 6, complete the table, graph the position versus the time, and sketch the actual path on an S number line. You should take the moment to pause the video, try the problems on your own, and then compare your answers to mine. If I make a mistake, or if you're not sure why I did something and you're getting something different, if you can't figure that out, send me an email and I will respond either by email or by making a little video and posting it, depending on what the question is and how in-depth I need to get. So at 0, we get 6. At 1, we get 3. At 2, we get 0. And at 3, we get negative 3. So when this thing started, my ant was 6 units to the right of 0. That was its position. 1 second later, it was 3 units to the right of 0. 1 second after that, it was at 0. And then 1 second after that, it went to negative 3. You can see that every second that goes by, the ant is going a distance of 3 units, but it's going to the left. And it looks like it's just going to keep going in that direction forever and ever. Again, the position versus time is not the actual path of the ant. The actual path of the ant is down here. The position versus time is just a graph that we make to help us visualize how the time and the position are related. So we make a time axis, we make a position axis, and then we graph the position versus time. This is the time, this is the position. And at 0, we're at 6. 1, 2, 3, 4, 5, 6. At 1, we're at 3. 1, 2, 3. At 2, we're at 0. And at 3, we're at negative 3. You should see by the equation that the graph is a line. So all these points should fall on one line. And there we go. Again, my graph should end there. In these problems, we're going to assume that time is positive. And so there we go. So S of t is negative 3t plus 6. Again, S prime of t. This is where the differential notation really comes in handy. ds dt, the change in position over the change in time. That's what that is. So that reminds us that this is a velocity. And so then this is a simple function to differentiate. The derivative of negative 3t is just negative 3. And the derivative of 0 is 0. And so what does this tell us? This tells us that the negative tells us we're going to the left, and that we are going to the left 3 units every second, which is what we saw when we looked at our actual path here. Every second that was going by, this was t equals 1, this was, I'm sorry, t equals 0, t equals 1, t equals 2, and t equals 3. Every second that increased, we walked 3 units. The negative told us that we were walking to the left. Getting a little bit more interesting, if the position of an equation for an ant that walks along a number line is given by S of t equals t squared minus 4, complete the table, graph the position versus the time, and sketch the actual path on an S number line. So S of t is t squared minus 4. When we plug in 0, we get negative 4. That tells us my ant starts 4 units to the left of 0. After 1 second, then it's at negative 3. 1 minus 4 is negative 3. After 2 seconds, then it is at 0. And then after 3 seconds, 3 squared minus 4, 9 minus 4 is 5. So when we started, we were over here at negative 4. 1 second, then we only changed 1 unit, and we got to negative 3. And then 1 more second goes by, now we're at 0. 1 more second goes by, and now we're at 5. Right? Notice that at first we only changed 1 unit, then 3 units, and then 5, right? And so we're just going, it looks like we're just going in this direction. It doesn't look like we're going to turn around. But as time keeps growing, we seem to be going faster, right? So again, position versus time. And so then at 0 we're at -4, 1, 2, 3, 4. At 1 we're at -3, 1, 2, 3. At 2 we're at 0. And then at 3 we're at 5. And we get a nice smooth parabola, not a line, not a constant rate of change. And so then every step we go up more. We go up more than the previous one. And so this is what this looks like. Find S prime of t. And what does it tell you in the context of this problem? So S of t is t squared minus 4. S prime of t, which again is the same thing as ds dt, the change in position over the change in time. And so now we're seeing that we don't get a constant value, we get 2t. The velocity is changing. And since we're only allowing positive values, this is always going to be a positive value, right? Or 0 when we start at 0. And so then as t gets bigger and bigger, 2 times t will get bigger and bigger, and so my ant is walking faster and faster to the right. That's what this tells me. If the position equation for an ant that walks along a numbered line is given by S of t is equal to 4 minus t squared, complete the table, graph the position versus the time, and sketch the actual path on an S numbered line. Now with that 4 minus t squared, at 0 we get 4. We start to the right of 0. At 1 we get 3. At 2 we get 0. And then at 3 we get -5. So we start over here at 4. 1 second goes by, and now we're at 3. We've moved 1 unit to the left. 1 more second goes by, then we're at 0. Now we've moved 3 units to the left. 1 more second goes by, and we're now at -5. And it looks like we're just going to continue to move to the left. So my ant is just walking to the left, going faster and faster. Right? The position versus the time. Zero, we're at 4. 1, 2, 3, 4. 1, we're at 3. 1, 2, 3. And then 2, we're at 0. And 3, we're at -5. Connect them with the parabola, nice smooth parabola. And you see that what this picture tells you is that as time moves forward, your position is decreasing, 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 and you're going faster and faster. So that tells you that you're moving to the left, right, on your S number line. So S of t was 4 minus t squared. So S prime of t, which is the same thing as ds dt, change in position over the change in time. And that is going to be negative 2t. And since we're saying that t is only a positive value, this will always be less than 0 or equal to 0. And that means that we are always moving to the left. But as we put in bigger and bigger values for t, the magnitude of the speed is increasing, so we're going faster and faster. That's why each second we cover a bigger distance. If the position equation for an ant that walks along a number line is given by s of t is equal to t squared minus 4t, complete the table, graph the position versus the time, and sketch the actual path on an s number line. Okay, so at 0 we get 0, so now we're starting at 0. 1 second, 1 minus 4, we move to the left, negative 3. 2 seconds, 4 minus 8 is negative 4. 3 seconds, 9 minus 12, we're back to negative 3. 4, we get 16 minus 16, we're back at 0. And then at 5, we're at 25 minus 20. Now we're moving, now we're going right. So we start here at 0. Move to negative 3. And then continue to negative 4. And from what we've done so far, it's not entirely obvious. If we go further to the left, or if we turn right back around at negative 4, but at 3 seconds we're back to negative 3. So we're only walking along the number line here. We're not walking off the number line, just going back and forth. That's all the ant is doing, but we can't really connect that, so we'll go off the number line and go like that. And then at 4 seconds we're back to 0, and then at 5 seconds we'll be at 5. When we look at the position versus the time, you should know just by looking at the equation, the graph is a parabola. This is what you learned in pre-calculus and in your other algebra classes, that your graph will be a parabola. So at 0 we get 0. At 1 we get negative 3. And then at 2 we get negative 4. Now it's not entirely obvious, but you do have a formula that allows you to find the vertex, and it turns out that that is the vertex, 2, negative 4. And then 3 we get back to negative 3, right? So this is nice and symmetric, so the vertex has to be right in between these, so it has to be here, and so at that point we got negative 4, that's my vertex. At 4 we get 0, and then at 5 we get 5. And so then what this tells me is that yes, this really was the furthest we went to the left. This point right here corresponds to this point right here. That's the furthest that we went to the left. So we started going to the left because all these are negative. We're going in the negative direction, going to the left. Once we get past this point, we start going up, which means we start going to the right. So this is the furthest that we went to the left. And then we turned around and went to the right. Find s prime of t. So s of t was t squared minus 4t. And so then s prime of t, which is also the change in position over the change in time, ds dt. And now we have the difference of two power functions. The derivative of this one is 2t, and the derivative of this one is minus 4. And so this tells me that my velocity, again, is not always constant, right? it's given to me by this expression 2t minus 4. And here the sign chart is going to kick in, and this is the sign chart for s prime of t. The only time that this is 0 is at 2. We're only interested in to the right of 0. We're not interested in to the left of 0. But the expression 2t minus 4 is only 0 at 2. To the left of 2, at 0, we get negative. That tells us that we're going to the left, right? And then once we get past 2, then we get a positive. So this is, again, another way of knowing that at 2, that was the furthest to the left that we were going to go, because that's what this sign function, sign chart tells you, that to the in between 0 and 2, we were moving to the left, and once we got past 2, we started moving to the right. So at 2, that was the furthest that we were going to go to the left. And so the other thing that the sign chart doesn't pick up on, though, is that once you get past 2, your velocities start increasing without bounding. You just keep going faster and faster to the right. So in everyday life, we interchange speed and velocity all the time, but in physics and in math, they are two separate things. The speed of an object is just trying to capture the magnitude of the velocity, how fast you're going, and not in what direction. And so then the speed of an object is defined as the absolute value of the velocity, which is what the magnitude, not necessarily what direction we're going in. Okay, so for s of t equals t cubed minus 6t squared plus 9t, find the velocity function and the speed function, and graph the position versus the time, the velocity versus the time, and the speed versus the time. Okay, so the velocity is just ds dt. Okay. And then that's just the sum of power functions, not very difficult to integrate. So then we get to differentiate 3t squared minus 12t plus 9. The speed function, we just take the absolute value, right? And so then speed function, just write it out, speed of t instead of s of t, because s of t is the position. So speed of t is just the absolute value of 3t squared minus 12t plus 9. And graph the position versus the time, the velocity versus the time, and the speed versus the time. Okay, so for the position versus the time, so we can use the velocity to help us figure out how many points we need there to graph the position, right? Well, that's what we learned the last time. So if we factor out the 3 from the velocity, if we factor out the 3, we will get t squared minus 4t plus 3. And then this will then factor as 3 times t minus 3, t minus 1. Okay. And so then what that tells me is that to graph my position function, all the key points happen first at 0, because that's where we're starting, then at 1, and then at 3. Putting this into your calculator, don't forget to label your tables, t, s of t, and then If you put that into your calculator, when you put in 0, you will get 9. When you put in 1, you will get 0. And, oh, I'm sorry, I put in the wrong one into the calculator. So let me go back and change this. Although, yeah. So when you put in 0, you will get 1. I should have known that that was wrong because this is a 1. All right, so now that we have this right, at 1 we get 5, and at 3 we get back to 1. The other thing that's going to help me graph my position function is the sign chart for the velocity. And so, again, not doing anything to the left of 0. And then we have 1, and then we have 3. To the left of 1, like 0, you will get negative 3 times negative 1, you will get positive. That tells us that we are moving to the right. Once you get past 1, then this one will switch, and you will have a negative times a positive, and you will get a negative. That'll tell us we're moving to the left. And once we get past 3, and then they're both positive, so we will be positive. Not going to worry about concavity, running short on space. So then this is t, and this is s. At 0, we get 1. And then from 0 to 1, we're going up, and we get all the way to 5. And then we continue that until we get to 3. And then, I'm sorry, once we get to 1, this will be as far up as we go for that part. And then we will come down, and we'll come at 3. At 3, we will get back to 1. Okay. And then once we get back to, once we get past 3, we start going back up again. And then we just keep going up forever. Not keeping track of inflection points or things like that. But here's what it's doing, right? Here's a quick sketch with only 3 points, and that's what we're going to be fine with. Graph the velocity versus the time, right? So the velocity versus the time, and then the velocity. Again, that's this function right here. At 0, we will get 9. At 1 and at 3, we will get 0. This is just a quadratic equation. And somewhere in the middle, we'll get our vertex. Graph ends there, goes on forever there. And when we graph the velocity function, right? I'm sorry, the speed function. So this is the speed. It's just the absolute value of this. And what the absolute value does is if you take the absolute value of a positive number, you get the same number. So all these numbers here, when you absolute value them, you get the same thing. Likewise, all these numbers here, when you absolute value them, you get the same thing. But these numbers here is the only spot where you're negative, and you're going to get the opposite. So your speed function looks like that. Okay, so if we want to graph the actual path, we see that my ant started here at an x value of 1. It walked to the right and ended up at an x value of 5 at a t value of 1. Then it walked back to 1 at a t-value of 3, and then it turned around and just kept walking to the left, to the right. From 0 to 1, it went from 1 to 5, and then from 1 to 3, it went from 5 back to 1, and then from 3 on, it just took off that way. This is the actual path. Of course, it would only stay on this number line, just going back and forth. It wouldn't come off the number line. That's why it's called rectilinear motion. Okay, so the change in velocity divided by the change in time is called the acceleration. So the acceleration is just the change in velocity divided by the change in time, delta V over delta T. At time t equals 3, the velocity of a particle is 5 feet per second. At time t equals 7, the velocity of a particle is 17 feet per second. What is the acceleration of the particle over the time interval? Include the units. So acceleration isn't a quantity that we use all the time in everyday life, so I just wanted to go over a very basic problem. So at time t equals 3, the velocity of a particle is 5 feet per second. So the change in velocity is 5 feet per second. Well, actually, it should always be where you ended minus where you began. And so you ended at 17 feet per second, and you started at 5 feet per second. And so 17 minus 5 is 12 feet per second. The change in time, your time was 7 when you ended, 7 seconds. And 3 seconds. And so then 7 minus 3 is 4 seconds. It took you 4 seconds to go from a velocity of 5 feet per second to a velocity of 17 feet per second. And so then your acceleration is the change in velocity, 12 feet per second, divided by the change in time, 4 seconds. And notice that 12 is divisible by 4, and so you get 3, but the units are feet per second per second. And to me, I like these units, right? Because it tells you that every second that goes by, your velocity changes by 3 feet per second. So that makes sense to me. But this is a complex fraction. You do have a fraction in a fraction. And so then what we could do is multiply the top and bottom by second, and you will get 3 feet per second squared. And that I don't really like the way it looks, but this is how most people write it. 3 feet per second squared. It doesn't, we don't usually talk about square seconds, but those are just units, right? I like the 3 feet per second. 3 feet per second squared is the conventional way of writing it. Okay, so if the position function is s of t equals t cubed minus 6t squared plus 9t plus 1, what is the acceleration function? Okay, so s of t is t cubed minus 6t squared plus 9t plus 1. The velocity function, which is just the derivative of the position function, the change in position over the change in time, is 3t squared minus 12t plus 9, which we said we could factor out at 3, and we said that we could then write this as t squared minus 4t plus 3, and this was then 3 times t minus 1 t minus 3. Okay. The acceleration is just the change in velocity over the change in time, which means that it is just the derivative of the velocity, and that would just be 6t minus 12. Now, earlier we made the sign chart for the velocity function. We're only concerned to the right of 0, 1, 3, and over here it was positive, and over here it was negative, and over here it was positive. And now we're going to look at what the acceleration sign chart looks like. This one's a line. You can see that the only number that makes it 0 is 2. 6 times 2 is 12. 12 minus 12 is 0. And to the left of 2, 1, 0, you're going to get a negative number. And to the right of 2, you're going to get a positive number. And we're not interested in this beyond 0. Okay, so if the position function is s of t is t cubed minus 6t squared plus 9t plus 1, what is the acceleration function? So this is the acceleration function, this is the velocity function. Right now, remembering that since the acceleration is the derivative of the velocity, and that the derivative function tells you whether the original function is increasing or decreasing, right? So right here where this is negative, this is telling you that your velocity function is decreasing. And right here where this is positive, then this is telling you that your velocity function is increasing, right? Because the acceleration is the derivative of the velocity. Okay, now if we look at the sign charts together, right? So right here your velocity is positive and this is decreasing, right? So this is like maybe you're at 8 feet per second and you're going down to 7 feet per second and 6 feet per second. So you're actually slowing down because these signs are opposites. But now if you look right here, both your velocity and your acceleration is negative. And so this is like if you're at negative 5 feet per second and you're decreasing, then you're going to negative 6 feet per second, negative 7 feet per second, negative 8 feet per second. And the magnitude of your speed is actually getting bigger. So your speed is actually increasing. Once you get past 2, now they're working against each other again because one is positive and one is negative. And so this is like now you're at negative 6, but you're increasing. So you're going to negative 5, negative 4, negative 3. And so those, the magnitudes are actually getting smaller until you get past 3, and then you're back in the positive, and then you are speeding up. So this is where students get a little confused because they automatically assume that if you're increasing, then you must be speeding up. And if you're decreasing, then you must be speeding down. I'm sorry, slowing down. That is not the case. What is the case is that if you are already positive at increasing, then you are speeding up. But if you are negative and increasing, then you are slowing down. Or if you are positive and decreasing, you are slowing down. That one's intuitive. But if you are negative and decreasing, then you are speeding up. And so that brings us to this very important result here. A particle in rectilinear motion is speeding up when its velocity and acceleration have the same sign, and slowing down when they have opposite signs. After you think about it for a moment, this should be intuitive, right? If you have the same signs, then you are working together, and so you will be speeding up. If you have opposite signs, then you will be slowing down. I quickly went through this slide, but this should be, let me go back to that. The acceleration we got by taking the derivative of the velocity. And the velocity we got by taking the derivative of the position. So then the acceleration is just the second derivative of the position. And the first derivative of the position is the velocity. Okay, let's move back. So we've already discussed that. We've looked at those sign charts. All right, so let's just formalize it real quick. So it looks like from 0 to 1, they're working against each other, so they're slowing down. And then so from 0 to 1, they were working against each other, slowing down. From 1 to 2, they're both negative, and so then they're speeding up. But now once we get past 2, between 2 and 3, they're working against each other again. You can see that this is negative and this is positive, so they're working against each other from 2 to 3, so they're slowing down. And then once we get past that, from 3 on, they're both positive, so then it's speeding up until whenever this thing ends. Okay. So the function s of t describes the position of a particle moving along a coordinate line where s is in meters and t is in seconds. Make a table showing the position, velocity, and acceleration to 2 decimal places at times t equals 1, 2, 3, 4, and 5. At each of the times in part A, determine whether the particle is stopped. If it is not, state its direction of motion. And at each of the times in part A, determine whether the particle is speeding up, slowing down, or neither. Okay, so the position s of t is equal to t raised to the fourth e raised to the negative t. The velocity is just the derivative of the position. The position is a product, so we have to use the product rule. I'm sorry, not 3. I bring down the exponent, 4t cubed, e to the negative t, plus, but the derivative of e to the negative t is e to the negative t times the derivative of the inside. The derivative of the inside will be -1, that's why this is a minus. And then we leave the first one alone, t to the fourth, e to the negative t. And then for what we're going to, there we go. Now, the acceleration function is the derivative of the velocity function. And so then we again have to use the product rule. We actually have 2 products. For this product, the first factor is 4t cubed. The derivative of that is 12t squared. And then leave the e to the negative t alone. And then minus, it's going to be a minus because the derivative of this factor is e to the negative t times the negative 1. And then we still have the 4t cubed. e to the negative t. Okay, and then we have the derivative of this, but if you notice, that is the same as this, and we already have that. So then we have minus, parentheses, 4t cubed e to the negative t minus t to the fourth e to the negative t. Make a table showing the position, velocity, and acceleration of the acceleration to two decimal places at times t equals 1, 2, 3, 4, and 5. Okay, and so then the easiest way to do this is to go and put this into your y equals, right? So you're going to use three different formulas. Y equals x raised to the fourth. Second, e to the negative x. And then 4x cubed. Second, e to the negative x minus x raised to the fourth. Second, e to the negative x. It'll be easier to put in the next one if you combine the like terms. And so then there's nothing to combine with the 12 x squared. Second, e to the negative x minus, but you are going to have 2 of the minus 4t cubed e to the negative x, and so then you'll have minus 8x cubed times e to the negative x, and then you have plus, when you distribute the minus, you will have plus x to the fourth e to the negative x. And then you can go to table set, and you can start at 1 and go up by 1 and have it do it automatically, and then you don't have to go and put the numbers in. T 1, 2, 3, 4, and 5. S, V, and A. And then to two decimal places, negative So I was getting a negative number for my first one, and I knew that there had to be something wrong. So the position is at 0.37. The velocity is at 1.1. and the acceleration is at 1.83. Since the velocity is not zero, the particle is not stopped. Since the velocity is positive, it is moving to the right, and since the acceleration is also positive, it is speeding up. At 2, we get 2.17. The velocity is 2.16. Since the velocity is not zero, it is not stopped. But the acceleration is zero, and so then what that tells me is that if there is no change in velocity, the object is not speeding up or slowing down, but it is moving to the right because its velocity is positive, but it's not speeding up or slowing down. At 3 seconds, we are at 4.03, and the velocity is at 1.34. Since it's 1.34, we are not, we are still moving. But my acceleration is negative 1.34. And so that tells me that we are slowing down because they have opposite signs. They're working against each other. Right? Moving on to 4 seconds. At 4 seconds, we are now at 4.6. Notice every time my position kept getting bigger because my velocity was positive and we were just moving to the right. But now my velocity is 0, and since my velocity is 0, we have stopped. But my acceleration is negative. I would argue that we are speeding up because when you have a position of, velocity of 0, and you have a changing velocity, you have an acceleration, then you are speeding up. Okay. And so even though they have opposite, well, 0 doesn't have a sign. 0 is neither positive nor negative. And then finally, at 5, we are now at 4.2. So we were at 4.6. 4.69, I'm sorry, I forgot the hundredths place. And now we're at 4.21. And then we have a negative velocity, negative 0.84. And we have a negative acceleration, negative 0.51. And so then we must be speeding up again because my acceleration and my velocity have the same sign. That is all we have for this section, section 4.6. Thank you very much. Bye.